Hey everyone, and welcome to The Explainer. There's a concept in precalculus that feels a little tricky at first, but honestly, it all boils down to one simple question. We're talking about horizontal asymptotes, and today we're going to crack the code and make them super simple.
Okay, let's dive right in. The entire idea behind horizontal asymptotes really comes down to this one thing. When you've got a massive fraction, and both the top part and the bottom part are just racing towards infinity, who wins? It's like this epic mathematical tug of war, and today I'm going to show you how to pick the winner every single time.
So, what is a horizontal asymptote, really? Well, simply put, it's the long-term trend of a graph. It tells us where the function is heading once x gets ridiculously big, either in the positive or negative direction. Think of it like an airplane. You've got that steep climb during takeoff, right? But eventually, the plane levels off at its cruising altitude. That flat, steady line way up in the sky, that's the horizontal asymptote.
So here's our flight plan for today. We'll start by digging into that infinity tug of war. Then I'm going to arm you with a super simple 3-rule toolkit. After that, we'll put those rules into action. I'll show you some common traps to avoid. And finally, we'll see where this math actually pops up in the real world.
So, how do we solve this infinity puzzle without getting a massive headache? The best part is, you don't need to mess around with complicated limits. All you need is one super powerful method called the degree comparison test. This is your go-to toolkit, and it's awesome. Believe it or not, this whole process comes down to 3 incredibly easy-to-remember rules. Meet your new best friends, BOB, BOTN, and EATS DC. First up, BOB. If the biggest exponent is bigger on the bottom of the fraction, the asymptote is always y equals 0. That's it, done. Next, BOTN. If the exponent is bigger on top, the top wins the tug of war completely and there is no horizontal asymptote. And last but not least, EATS DC. If the exponents are the same, you just divide the leading coefficients. That's the whole game, right there.
Okay, but why does this actually work? Is it just some weird math magic? Not at all. Here's the key. When x is a huge number, I'm talking a million, a billion, whatever, the terms with the highest exponents have all the power. They do all the heavy lifting. Everything else, all the smaller terms, they just become, as the source material perfectly says, meaningless dust. You only need to focus on the strongest players in that tug of war.
All right, theory is great, but math is all about doing. So let's put our new 3-rule toolkit to the test with a few examples.
First up, a pretty standard one. We need to find the horizontal asymptote of f of x equals 5x plus 1, all divided by x squared minus 4.
Okay, let's follow the process. Step 1, we find the biggest exponent on the top and bottom. On top, it's just x to the power of 1. On the bottom, it's x squared, so a power of 2. Step 2, we compare them. 1 is definitely less than 2. The bottom is bigger, which means we have a classic Bobo case.
And because it's bigger on bottom, the answer is just y equals 0. The x-axis is our asymptote. Simple as that.
All right, let's try another one. Let's find the horizontal asymptote for g of x equals 6x squared minus x, all over 2x squared plus 5.
So, same deal. Let's look at the degrees. The highest exponent on top is 2. The highest exponent on the bottom is also 2. It's a tie. So what do we do when the exponents are the same? You got it. It's time for EATS DC. We ignore all that other meaningless dust and we just divide the coefficients, the numbers in front of our strongest terms. So in this case, that's just 6 divided by 2.
And that gives us our horizontal asymptote, y equals 3. This graph is going to level off at a height of 3.
All right, one last case to really lock this in. Let's analyze the end behavior of h of x equals x cubed plus 1 divided by x minus 2. Okay, one last time, let's look straight at the degrees. The top has a degree of 3. The bottom only has a degree of 1. Well, 3 is way bigger than 1. The numerator here is an absolute powerhouse. It's going to win that tug of war every single time, no contest.
And that, of course, is our BOTN case. Bigger on top means none. The graph never settles down, it just keeps growing forever, so there is no horizontal asymptote.
Now that you've got the 3 rules down, you're pretty much set. But let's quickly go over the biggest mistakes people make just so you can be sure to avoid these traps. This is, without a doubt, the most important trap to avoid. Do not mix up vertical and horizontal asymptotes. A vertical asymptote is like a brick wall. It's a place the function can never, ever exist, so the graph can never cross it. But a horizontal asymptote is different. It's all about the end behavior. Think of it more like a suggestion for where the graph is heading way out at the edges. And here's the kicker. A graph can absolutely cross its horizontal asymptote, usually somewhere in the middle.
Okay, I know what you might be thinking. This is a neat math trick, but is it ever actually used for anything? The answer is a huge yes. Let me show you a really cool application.
Let's look at pharmacology. The concentration of a drug in your bloodstream over time can often be modeled by a rational function, just like the ones we've been looking at. As time, or t, goes on and on towards infinity, what do we see? The degrees on the top and bottom are the same. It's an EATS DC case. And that horizontal asymptote isn't just a random line on a graph. It represents something real. It represents the maximum saturation level, the absolute limit of the drug the body can absorb.
And that kind of brings us full circle to a really interesting final thought. If we know a graph can cross its horizontal asymptote, what does end behavior truly mean? It's a great reminder that this whole concept isn't about what's happening right now in the middle of the graph. It's about the ultimate long-term trend as we journey out towards the infinite. It's not just about where the line is, but where it's going.